Radius of isoelectronic species. Radius of isoelectronic species. Isoelectronic species. Atoms are ions. Isoelectronic species. Isoelectronic species. Atoms are ions. Atoms are ions. Are those which have the same number of electrons. Are those which have the same electrons, same number of electrons. Which have the same number of electrons. For such species, the radius decreases with an increase in atomic number. If the atomic number increases, then radius. If radius decreases, then radius decreases. Atomic number increases, then radius decreases with an increase in atomic number due to an increase in effective nuclear charge. Due to increase in effective nuclear charge. Due to increase in effective nuclear charge. Effective nuclear charge. This variation of radii of isoelectronic species is given isoelectronic species. Isoelectronic species. Atomic number Z and number of electrons. Atomic ionic radii angstrom. Atomic or ionic radii in angstrom. This is the isoelectronic species. This is the atomic number Z. This is the number of electron, and this is the ionic radii in angstrom. C4 isoelectronic species. C-4 N-3 oxygen -2 fluorine minus neon sodium plus magnesium +2 aluminum +3 and so on. Atomic number of Z, carbon 6, number of electrons 10, because 6 is its own electron, and 4 minus 4 means 4 electron gain by carbon. 4 electron gain by carbon, then the 6 4 how many? 10 and atomic ionic radii in angstrom 2.60 and nitrogen -3 or 7, total number of electron 10 and atomic or ionic radii 1.71. Oxygen 8, fluorine 9, neon 10, sodium 11, magnesium 12, and aluminum 13. Total number of electron 8 to 10. Total number of electron 9 1 10, and neon total number of electron 10. Total number of electron 10. Sodium total number of electron 11, and one electron is released by sodium, then one electron is subtracted by 11, then the value is 11 minus 1, 10. Number of electron 10. Magnesium have 12 electron, total number of electron, atomic number 12, so total number of electron 12, but magnesium 2 electron releases, so 2 electron is minus by 12, then 12 minus 2 equal to 10, and aluminum 13 minus 3 equal to 10 number of electrons, and ionic radii of oxygen 1.40, ionic radii of fluorine 1.36, ionic radii of neon 1.12, ionic radii of sodium ion 0.95, ionic radii of magnesium radium, ionic radii of magnesium 0.65, ionic radii of aluminum 0.50, and so on. And next is determination of covalent radii. Determination of covalent radii. Determination of covalent radii. Determination of covalent radii. The distance between the atom of covalent molecules atoms of covalent molecules the distance between the atom of covalent molecules is determined with the help of X-ray, electron diffraction, and spectroscopic methods. The distance between the centers of adjacent atoms. The distance between the center of adjacent atom. The center of adjacent atom. The distance between adjacent atom is called internuclear distance. It's called internuclear distance. The half of the internuclear distance is the half of the internuclear distance. The half of the internuclear distance is called covalent radius. Is called covalent radius. And next is homonuclear diatomic molecules. Homonuclear diatomic molecules. Homonuclear diatomic molecules. Homonuclear diatomic molecule. Homonuclear diatomic molecule. Diatomic molecule. Diatomic molecule A2. Homonuclear diatomic molecule. In this case, two similar atoms are bonded together by a covalent bond. In this case, two similar atoms are bonded. Two similar atoms are bonded. Two similar atoms are bonded together by a covalent bond. Together by a covalent bond. So bond length are internuclear. Internuclear distance is given. Internuclear distance is DAA equal to RA plus RA equal to 2RA. Then RA equal to DA minus A DAA upon 2 where RA equal to covalent radius of A. RA equal to covalent radius of A. Covalent radius of A. For example, for H2 molecules, DA is equal to, for H2 molecules, DAA means homonuclear diatomic. DAA, homonuclear diatomic, is equal to 0.79 angstrom. Is equal to 0.79 angstrom. Hence covalent radius of H atom. Hence covalent radius of H atom equal to 0.74 upon 2. 0.74 upon 2 equal to 0.37 angstrom. And next is a heteronuclear diatomic molecule. Next is heteronuclear diatomic. Heteronuclear heteronuclear diatomic molecule. Heteronuclear diatomic molecule. Diatomic molecule. AB. When two different atoms A and B are bonded together by covalent bond and their electronegativity value is different, the bond length is determined by Isomaker and Stevenson method 1941 as follows: DEA equal to RA plus RB minus C chi A minus chi B. Then the value is when two different atoms A and B, when two different atom A and B, two different atom A and B are bonded together by atoms are bonded together by covalent bond and their electronegativity. Covalent bond and their electronegativity values are different. Electronegativity values are different. The bond length is determined by Isomaker and Stevenson method in 1941, where is DAB equal to RA plus RB minus C chi A minus chi B, where C is Isomaker and Stevenson constant, where this is the C, where C is Isomaker and Stevenson constant. Chi A and chi B are the electronegativity of atom A and B. Chi A and chi B. Chi A and chi B are electronegativity of atom A and B. Electronegativity of atom A and B. Calculation of bond length DAB for heteroatomic molecules. Pauling has given following formula: DAB equal to RA plus RB minus 0.09 chi A minus chi B. Chi A minus chi B The half DAB is called covalent radius of AB heteronuclear molecules. The half of DAB, the half of DAB is called covalent radius. Is called covalent radius. Covalent radius is called covalent radius for AB heteronuclear molecules. For AB heteronuclear molecules. Heteronuclear molecules. And next is determination of ionic radii. And next is determination of ionic radii. Next is determination of ionic radii. Next is ionic radii. Determination of ionic radii. Determination of ionic radii. The determination of ionic radii has been given by X-ray diffraction. The following two methods have been used for the determination of ionic radii. First is Linde method. First is Linde method. Linde method. First is Linde method. When in ionic crystal, when in an ionic crystal, the anion is very bigger in comparison to cation. The anion is very bigger. The anion is very bigger. The anion is, in Linde method, the anion is very bigger in comparison to cation. In comparison to cation. Then anion will be in contact in. Then anion will be in contact in crystal. In contact in crystal lattice. Lithium plus ion in Li is shown in the figure. Lithium plus ion and iodine minus ion. Lithium iodide in Li capital I. Lithium iodide by experiment according to figure BC square equal to AB square plus AC square. AB square plus AC square. Then the value is 6 square plus 6 square equal to 72 angstrom. But AB equal to AC equal to 6 angstrom edge length. 6 angstrom edge length. Then the BC equal to under root of 72 angstrom. But BC equal to 4 R negative. So 4 R minus equal to root 72 angstrom. Then the R minus equal to 6 upon 4 root 2 angstrom. Equal to 2.12 angstrom. Hence ionic radius ionic radius, hence ionic radius of iodine ion is 2.12 angstrom. In crystal of Ki anion and cation in contact with each other. This is shown in the figure. And in next we are study about this function. But in next we are study about this function. And next is Pauling method. Second is Pauling method. Second is Pauling method. Pauling method. Second is Pauling method. Pauling method. Pauling method. Second is Pauling method. This method depends upon two concepts. This method depends upon two concepts. First is cation and anion are assumed to be in contact. Cation and anion are assumed. Cation and anion are assumed to be in contact. Then R0 equal to R cation plus R anion. And B, next method is for a given inert gas, configuration the radius is assumed to be universally proportional to the effective nuclear charge. Effective nuclear charge. Then R equal to C by Z conjugate. Where Z conjugate equal to Z minus S equal to effective nuclear charge. Effective nuclear charge, and C equal to proportionally constant. Proportionality constant. Then the value is R cation upon R anion equal to C by Z conjugate upon C by Z conjugate equal to C upon Z conjugate cation and C upon Z conjugate anion equal to C upon Z conjugate cation into Z conjugate upon C anion. Z conjugate anion upon C equal to Z conjugate anion upon Z conjugate cation. Z conjugate cation, where Z conjugate equal to effective nuclear charge of an ion. Effective nuclear charge of anion, and Z conjugate of plus cation means effective nuclear charge of cation. Pauling choose some isoelectronic ion pairs examples. Pauling choose some isoelectronic ion pairs as an example: NaF, sodium fluoride, potassium chloride, magnesium bromide, and cesium iodide, CSI. With the help of this, we can easily calculate the ionic radii. For example, for the calculation of ionic radii, for the calculation of ionic radii, of sodium cation and fluorine anion, we consider the isoelectronic we consider the isoelectronic ion pair NaF, sodium fluoride. Experimentally, the intermolecular distance R0 for NaF is 2.31 angstrom. Effective nuclear charge for the ion can be calculated by Schlatter's rule. Z conjugate sodium cation equal to 11 minus 2 multiply 0.85 plus 2 multiply 0.30 plus 6 multiply 0.35 with the rule by the help of rule of Schlatter rules. Then the value is 11 minus 4.40 equal to 6.60, and Z conjugate for fluorine anion equal to 9 minus 2 multiply 0.85 plus 2 multiply 0.30 plus 6 multiply 0.35 equal to 9 minus 4.40 equal to 4.60. As we know, R equal to C upon Z conjugate, then R plus, that means R cation equal to C upon 6.60 and R anion equal to C upon 4.60. Hence C upon 6.6 plus C upon 4.6 equal to 2.31. Then the value is 4.6C plus 6.6C upon 6.6 multiply 4.6 equal to 2.3, and then solve the value C equal to 6.262. Then the value R Na plus equal to C upon Z conjugate Na plus ion equal to 6.26. 2 upon 6.6 equal to 0.948, approximate 0.95 angstrom. And Rf equal to C upon Z conjugate F fluorine minus equal to 6.262 upon 4.6 equal to 1.36 angstrom. Hence ionic radius of Na plus ion is 0.95 angstrom, and ionic radius of fluorine minus ion is 1.36 angstrom. And next heading is ionization potential or ionization energy. Okay.